Okay, this is WebAssign 10F, problem number 6. The pair of capacitors in the figure below are fully charged by a 14-volt battery. The battery is disconnected and the switch is then closed. After 3.1 milliseconds has elapsed, how much charge remains on the 3 times 10 to the 6 farad capacitor. Okay, cool. Alright, so we have 2 capacitors in parallel. So is actually, we can treat that as one capacitor by adding both of the the capacitances together. So it basically looks like this now, and we have removed the battery, so I'm not going to draw the battery or the switch because the switch is closed. Okay, so now this is basically our system. So we have 5 farads. I'll do sig figs. Okay, cool. And then this is 500 ohms. This is the same. Right. So, we don't know initial charge. We need final charge. And we can find initial charge and we can find our time constant. So actually the formula we'll be using, it's a final charge will be equal to initial charge times e to negative t divided by our time constant, and we know our negative lowercase t, and that is our 3.1 seconds. And yeah, okay, so to find this initial charge, we're going to do our charge is equal, okay, well, let me do it here. Capacitance is equal to charge over volts. Therefore, Q is equal to volts times capacitance, and seeing as no, it's only a resistor and a capacitor in this system, we can use 14 volts as our voltage. So our Q is equal to our 14 volts times our capacitance, which is total capacitance, which is 5.0, and it's going to be 5.0. Even though I am solving for the 3, I'll just multiply by 3/5 because that's the ratio of the 2 capacitors. So that is that. So then we now have our initial charge. This initial charge is equal to 70 times 10 to the 6. I'm just going to write it like that. Coulombs. Right? Yeah, cool. And that's just for our initial charge. So now we need our time constant. We know our time constant is equal to RC, which is resistance times capacitance. We have a resistor, we have a capacitor. Our resistor is 500 ohms, and our capacitor is again this. Yeah, it's this 5.00, and I'll just use this rating of it, and then that is it's 0.0025 seconds, so I'm just going to put it in the milliseconds, so 0.25 milliseconds. Seeing as our 3.1 is in milliseconds, that'll just be easier. Okay, now we can plug this all into our equation, which is our Q initial. Q initial was 70 times 10 to the negative 6, or I said negative 6 coulombs. E to our negative t, which is going to be negative 3.1, because that's the time it gives us, negative 3.1. This is milliseconds. Divided again by another milliseconds, which we just found is 2.5. So I don't have to worry about their, I don't have to worry about how their units would correlate, because it's basically 1-to-1 the unit sense, so it's just 3.1 over 2.5. And then we get an initial charge of whatever written. I think my answer after I worked it out, as you can see, I got it wrong, but after I actually worked it out the right way, I got 12. The correct answer is 12.2. And actually, the reason I did it wrong was because my time constant was wrong. I think I multiplied by. I don't think it was capacitance I multiplied by. I think I multiplied. I did. I think the resistance times voltage. I did something like stupid. Even though I had RC, I think I just looked at the wrong unit the first time. So it took me 5 attempts, and I got different answers each time. And obviously, you can see I ended up getting it wrong. But actually no, this will not equal 12. Hold on. No, this equals like 20. Yeah, this equals 2 times 10 to the negative 5th. Or at least that's what my calculator states it. But that's not the right answer. So yeah, it equals 20. So yeah, you can see I have the 19 more before. I don't think that's I don't think I forgot to multiply 3/5. I did multiply by 3/5, and I got 19.44. So you couldn't just say, oh, let's multiply that by 3/5, you get 12. No, I just did it completely the wrong way. So yeah, back to this. So this is 2.5, and now I multiply by 3/5 because that's the ratio of the capacitors. And now I get, once I plug in my calculator, 12 times 10 to the negative 6. Well, yeah, 12, this unit. So that's how I got the 12. See, even just now, I forgot to multiply by 3/5, and I was looking at my answers, and then just immediately assume that's what it equal, but no, you gotta multiply by 3/5 to get the ratio. And then a quick trick for part B, knowing that this is like, knowing this, we can just quickly multiply this total again by 2/5, and then I'll get the answer. Or we could just subtract this 12 value minus, this 20 value minus the 12, because 20 is the total minus the 12, and that'll give us about 8. As you can see, it's 8.133, and I didn't worry about my units because I knew they were both in microcoulombs. Or is it? I don't know, I'm probably messing that up, but I do have 2 times 10 to the 5th. Well, 10 times 20 to the negative 6. It's the same thing. That's why I was able to just do it, with no units down here. And then what is the current and resistor at this time? Okay. So this part actually, after my, I messed up everything before that. I actually got this part pretty quick. I was actually pretty happy with the way I did it. And looking at my notes now, I don't see where I did it. Yeah, I do. Okay, cool. Voltage is equal to charge over coulombs, right? It's basically the same formula I used. Not basically, it is. It's the same one I used, like, up here. But yeah, it can't be the 14 volts because our battery is no longer connected to the system, so it's only the volts that exist inside the capacitors. So this voltage from the capacitors is equal to our charge, which we just found, which would be 20. It's entirely 20 if you want to do it in one take and not divide into 2. So it would be 20. Then here's my decimal approximation that my calculator showed me. There's 10 to the negative 6. That would be coulombs again. Divided by our total capacitance, which is 5 times 10 to the negative 6 farads. So then this voltage is actually 4.066. So it's not all the 14 volts from our system because the capacitors can't really take all that voltage. Once they equal out, that's as much as they're going to get. So then we use that to find our current using this resistance. So then we use V equals IR. And then we rewrite that, so I equals V over R. But now it's using this voltage we just found. So it's not V. I is equal to 4.066. And again, I'm not worrying about my units because these are both negative 6, so it'll just be 20.33 divided by 5. This is 4.66 volts. And then divided by our 500 ohms, so our current in this unit, it's milliamps, so the answer I actually would get was 0.008132 amps, I believe. And then milliamps would then be multiplied by 1,000, 0.132 amps, milliamps, and that is again the answer I got up there. So main takeaway from this, you just gotta know the basics. You just gotta know capacitors in parallel. You just add them up to get the total here. This formula, it was in the video. It took me a minute to actually find it to be able to utilize it, but once you know that formula, the whole thing is pretty straightforward. Just gotta remember what your time constant equals. You just gotta remember, some of these basic ones that you might forget, or you might forget the order of how they're arranged. And just make sure you're looking at the units attached to these, so then you can figure out which one's capacitance, which one's resistance. Because like I said, I messed up this one because I was looking at the wrong units the whole time, and I kept plugging in the wrong numbers, and then, evidently that cost me a point. But once I went from that point, I knew what I had to do from there on. So sometimes just about getting that first part done correctly, and just carry that energy to the next two, and you'll be set. But when you do get that first one wrong, you just gotta maybe walk away for a few minutes and come back and see what you did wrong. That's what I did. I came back, I redid the problem, I got different got from time constant answer, and I was like, dang, really? That's all it was? Because I had assumed I did that correctly, and everything following that was wrong, because that's probably one of the easier steps. But that was actually the one part I did wrong. So once I went back and fixed that, the whole thing was a breeze. So just gotta watch the little mistakes to make sure you don't make any big ones.